Alrighty, in this video we're looking at roots of complex numbers, and if you're comfortable with Demoivre's theorem, then you'll be hopefully comfortable doing this. So remember, Demoivre's theorem told you that basically if z was r cis theta, then z to the n was r to the n cis of n theta. And that just comes from the definition of times in complex numbers. So that would tell you that if you put n equals a half, it would still work. So this doesn't just work for whole numbers, it works for basically anything. So that's basically what we're going to use to find square roots of complex numbers, because if you see something like this one here with root of -1 plus I, well, you wouldn't really know how to do that without using polar form. So first thing we need to do is basically say let z equal -1 plus I. Mod z would then be square root of -1 squared plus 1 squared, which is root 2. Basically, what we're doing here is converting into polar form. Now, if we want argument of z, we're going to start by finding inverse tan of 1 over 1, which is pi over 4. But we need to adjust because we're sitting over here, and we're going to have to do pi take pi over 4 would give us that angle there. So argument of z is pi take pi over 4, which is 3 pi over 4, just like that. So z is going to be root 2 cis of 3 pi over 4. Okay, so then if I want to find root z, essentially, it's going to be square root of root 2 cis of a half 3 pi over 4. So that's going to be, well, that's the 4th root of 2, cis of 3 pi over 8. And that would be how this works. So that's a bit of a tricky one, but sometimes what's a bit easier is doing these roots of unity questions because the modulus and arguments are really nice. So what we want to do is solve z cubed equals 1. So I can write z in polar form. So let z equal r cis of theta. Then z cubed is going to be r cis of 3 theta, just like that. R cubed cis of 3 theta. Now, if I write 1 in polar form, that's going to be cis of 0. So basically what you're trying to do is you're trying to compare these two angles. So you can write 1 in lots of different ways. So it could be 1 equals cis of 0, or it could be cis of 2 pi, or it could be cis of 4 pi, or it could be cis of -2 pi, because you can always add or take a multiple of 2 pi. So if I write 1 equals cis of 0 plus 2k pi, that's going to be basically what we need. So if we compare this out, z cubed equals 1 becomes r cubed cis of 3 theta equals cis of 0 plus k2 pi. Then we just compare the arguments and the moduli. So r cubed would have to equal the 1 because there's a 1 there technically. So r equals 1. And then 3 theta equals 0 plus k2 pi, just like that. So what we need to do is find our value of theta. So if we want to do that, theta could be 0 plus k2 pi over 3. Yeah, so now what we basically do is we sub in lots of different values of k until we find all the values of theta that we could have. So essentially what you're going to do is you're going to set k equal to 0, and you're going to get theta equals, well, 0 over 3. If k equals 1, we're going to get theta equals 1 lot of 2 pi over 3. If k equals 2, then we're going to get theta equals 2 lots of 2 pi over 3, which is 4 pi over 3. But given that our theta always has to be in between minus pi and pi, that's actually banned because 4 pi over 3 is bigger than pi. But if k equals -1, I get theta equals -2 pi over 3, which is good. But if k equals -2, again, we have that issue. Theta equals -4 pi over 3, which is banned. All right, so we found 3 answers. So those are our 3 answers. Z is going to be cis of 0 or cis of 2 pi over 3 or cis of minus 2 pi over 3. Just like that. Okay, so there's actually 3 answers, and that's because this is a cubic equation. So if you're familiar with quadratics, you know quadratics always have 2 solutions. Turns out cubics always have 3, quartics always have 4, and so on. And this is how it works. This is an example of the 3 numbers that when I cube them, I'll get 1. So let's actually check and see if this works. So maybe if I just do this one here, cis of 2 pi over 3, and if I cube that, I'm going to get cis of 3 times 2 pi over 3, which is going to give me cis of 2 pi, which is the same as cis of 0, which is 1. So there's actually 3 answers here. And if you draw them on the complex plane, it ends up being pretty cool. So you basically got your complex plane will be sitting here. And we know we're trying to solve the equation z cubed equals 1. So we've got one answer sitting there, which is 1. 1 cubed equals 1. Now, cis of 2 pi over 3 sort of sits out like here-ish with an angle of 2 pi over 3. And then down here is cis of minus 2 pi over 3. So if you imagine I take this angle here and I triple it, I would get back to 1. Same as if I take the clockwise angle here and triple it, I would get back to 1. Those are our 3 roots of minus 1. It's pretty cool stuff. And it turns out that if you draw this out properly and connect them all up, it actually makes an equilateral triangle, which is a nice fun fact for us. So it works for 4th roots of unity and 5th roots of unity and so on. You'll never guess what you get if you do 4th roots of unity. It's pretty cool. So that's taking roots of complex numbers.